Welcome. In this video, we're going to troubleshoot RS232 serial communications on the LX200 classic telescope. This serial port allows control of the telescope by third-party planetarium programs, as well as other software programs. To set up for this, we'll need access to the powered-up electronics of the LX200 main CPU board, static protection, a serial adapter cable, and a computer with some serial communication software to test with. We'll also need a DVM and an oscilloscope. So here we have the LX200 CPU board connected to its RA drive assembly, front panel with all of the connectors, and a handset. We need all of these connected up for the LX200 to be able to communicate with the outside world. Here's a high-level look at the LX200 serial communications. The 68301 CPU is configured with two serial ports operating at 5-volt logic levels, and both are available on the front panel connector. But we're only going to be concerned with the primary port. The CPU port connects directly to the MAX232 IC, which translates the logic levels to RS232 levels. After the MAX232, the signals then connect to the outside world via the RJ-type connector labeled RS232 on the front panel of the telescope. Throughout this video, we'll be using the color yellow for the commands being sent to the telescope and green for the response coming back from the telescope. We'll connect the telescope to our PC using a USB to RS232 adapter cable that has the proper pinout for the LX200's RS232 connector. We're using the Clearline LX200 USB adapter, but other options will work as well. The LX200 provides two RS232 ports in the same 6-pin connector on the front panel, but as mentioned, we're only going to work with the primary one. We need only 3 pins: PC transmit, PC receive, and ground. PC transmit means data is coming from outside into the telescope, and PC receive means data coming out from the LX200 to the connected device. This view is looking into the connector from the front of the telescope with the connector tab down. Now that we've connected up our PC to the telescope, let's test a few commands. We're using a program that knows about the LX200 command set, but we could have used other serial communications programs to send the raw byte sequences for these commands. They're all documented in the LX200 manual. Some commands are one-way directives to command the scope to move, for instance. They don't generate a response from the telescope, and we'll try some of those first. We'll first try moving the RA drive to the east. We can hear the motor running, so we know that the command worked. Next, we'll change the slew speed, and that worked as well. Now let's try a two-way command, one that requires a response back. These commands should return the time and the coordinates, but it looks like nothing was sent back from the LX200. Going back to our block diagram, let's look at what seems to be happening. The bytes we sent from the PC, in yellow, appear to be getting through and being correctly handled by the CPU, since we heard the RA drive move when we commanded it to. Yet, we're not seeing anything returned by the LX200. Why would that be? There are a few places the problem could be. For one thing, the CPU may not be sending the response, or the MAX232 may not be correctly converting them, or there may be an open circuit due to a bad connector or PCB trace. Let's see if we can narrow it down. Before we start probing, let's review the signals we should be seeing. Between the CPU and the inward-facing side of the MAX232, we should see normal logic levels, around 4.5 volts for a logical 1 and around 0.4 volts for a logical 0. At the outward-facing pins of the MAX232, we should see RS232 level signals, which are higher and lower than 5-volt logic, and also inverted. These need to be at least 3 volts and at most 15 volts for a logic 0, and at least minus 15 volts and at most minus 3 volts for a logic 1. Anything less than 3 or greater than negative 3 is invalid. From the MAX232 datasheet, we see that the typical values it transmits are +9 and -9, which we've used for our sample waveform in this drawing. But the exact bit patterns are not important at this step. We're just looking for activity. This is a block diagram of the MAX232 with pin numbers. We only need to worry about the 4 pins that pass data back and forth to the PC on port 1. Here those are labeled T1 in, T1 out, R1 in, and R1 out, and they correspond to pins 11, 14, 13, and 12. T1 out and R1 in are the outward-facing pins. T1 in and R1 out are the inward-facing pins. All of the signals we want to look at are present on the MAX232 pins. Fortunately, they're large and will be easy to probe. The yellow line here is the signal coming from the PC into the CPU, and the green line is the signal coming back from the CPU to the PC, just like on our block diagram. Though we already know that data is correctly coming in from the PC, let's probe there first just to see what's going on. We'll start by probing pin 13 to see the RS232 level signal coming in from the PC. These logic levels are valid RS232 levels at about plus and minus 5 volts. Note that we're set up to trigger on about 1 volt. Our vertical scale is 5 volts per division, and our horizontal scale is 400 microseconds per division, since this is a slow 9600 baud serial protocol. Now we'll probe pin 12 to see our signal further on the way in on the yellow path to the CPU. This is R1 out, the signal from the MAX232 to the CPU. And we see the signal made it through, being converted to 5 volt logic levels the CPU can understand. This is working as expected. Now we'll probe pin 11, which will show any response coming back from the LX200's CPU to the MAX232 on its way out. In this case, we sent the command to get the sidereal time, so we do expect a response from the telescope. This is the first leg of the green path. And we do see a response from the CPU with the correct 5 volt logic levels. So we've eliminated one of our possible failure modes, the CPU chip. This is great news, because this IC is expensive and hard to find. Finally, we probe pin 14, which should show the RS232 level signal being sent back to the PC by the MAX232. Here, we can't find an RS232 level signal after several tries. The signal never goes below 0 volts, when it should fall to lower than -3 volts. It seems then that the MAX232 has failed, and although there are still some other possibilities, we've checked the connector and trace connectivity already with the DVM. Looking at the MAX232 datasheet, we note that 4 capacitors are necessary for generating and holding the high and low voltages needed for the RS232 signal levels. On our LX200, these are all 6.8 microfarad, and they've been newly replaced, so they're probably okay. We can directly measure these generated voltages on pins 2 and 6, so we'll do that. The datasheet shows they should be 10 volts at pin 2 and negative 10 volts at pin 6. First, probing pin 2, which we expect to be around positive 10 volts, we're only getting around 4.5 volts. That's out of spec for the chip, but 5 volts is still a valid RS232 logical level, so this might still be okay. Probing pin 6 though, instead of minus 10 volts, we see a positive voltage. That's definitely wrong, and checking with the datasheet, we see that the absolute maximum voltage that pin 6 can tolerate is 0.3 volts. We read much higher than that here, so this chip is probably damaged. We now have some pretty good evidence that the MAX232 chip on this board is bad, and our next step will be to replace it. Be sure to look out for a video on that. We hope you found this one interesting. If you have questions or suggestions, please leave a comment below. Thanks for watching.